Good afternoon. So, we were discussing regarding the modifications which are generally done to the basic Brayton cycle. Now, the first thing what we have discussed, that the exhaust which comes out of the turbine, that will still have enough thermal energy which can be utilized. If we do not utilize it, it is going to the ambient atmosphere. Not only we are wasting a potent source of energy, but also we are creating some amount of thermal pollution. So, what I have told that with this thermal energy, the compressed air can be preheated, and then the preheated air can be sent to the combustion chamber. Now, this increases the efficiency of combustion, and obviously, you have to burn less amount of fuel. So, what we are having, I will quickly have the block diagram. First the compressor, then from the compressor the stream is being preheated, then after that it is going to the combustion chamber, where we have got fuel spray, then it is going to the turbine which is generating power, then this one is the exhaust gas, and ultimately through the regenerative heater it is going to the ambient atmosphere, and this is again ambient atmosphere. So, if we want to show a closed cycle, then this will be something like this. After this, this is again going back to the this is one unit where you are rejecting heat, and after that it is going to the compressor. If we show a closed unit, it will be like this. This is an idealized representation of the gas turbine cycle with regenerative heating. Okay. Let us put 1 here, then after compressor it is 2, then this is 3, this is 4, this is 5, this is 6, this is 1. So, PV diagram will be 1 to 2 compression, then 2 to 3 or 2 to 4 heat addition at constant pressure, then 4 to 5 expansion, and 5 to 1 heat rejection at constant pressure. So, 1, 2, then 2 to 4 I told 4, 4 to 5 and 5 to 1. Only thing is that in between we have got 2 to 3 and then we have got 5 to 6. So, this is internal, that is what I have told in my last class. But why again I am repeating? There is a reason how to analyze this cycle. We will not go into a rigorous analysis, but let me try to give some sort of an hints that what can be done for the analysis. What can be done for the analysis? This heat exchanger now plays a very important role in the performance of the cycle. So, this is regenerative heat exchanger, or we can call it regenerator. So, this plays a very important role in the performance of the whole cycle or entire cycle. And for this heat exchanger, we can have some sort of effectiveness defined. We know what type of heat exchanger we are using. So, we can define some sort of effectiveness for this heat exchanger. Actually, heat exchanger effectiveness, that may be a slightly new term, or probably you are familiar with it. Unfortunately, we do not have much time, so that we could have discussed it in details while we will study while studying heat transfer, but probably we will not have that time. It is like this. In a heat exchanger, let us say this is the schematic representation of a heat exchanger. This is one stream of fluid, this is another stream of fluid, and they are exchanging heat. Right. Now, this heat exchanger, let us say this is hot gas, it is coming at THI inlet, going out at THO outlet, and this is cold gas or cold fluid TCI and TCO. So, inlet and outlet temperatures. Now, one can from this determine what is the maximum possible amount of heat transfer. What is maximum possible amount of heat transfer in this case? So, for that one has to know what is the medium and what is the property of the medium, and let us say let us say we can have for this m dot H is the mass flow rate of the hot fluid, and Cph is the specific heat of the fluid, hot fluid. Then m dot C is the mass flow rate of the cold fluid, and Cpc is the specific heat of the cold fluid. Then we can get what is the heat transfer by the hot fluid and what is the heat transfer for the cold fluid. They will be the same quantity, but we will get two expressions. Okay. Now, what we can get, m dot q dot is equal to m dot c Cpc into, for this there will be temperature increase. So, we can have Tci, this is the rate of heat transfer, and this will be identical to m dot H Cph and Thi minus Tho. Thank you. So, this will be the heat exchange by the hot fluid. Now, which temperature will be or which change in temperature will be higher? No, we cannot say that whether it is cold medium or hot medium. We can only say for the medium for which this product is small, for that we will have the highest temperature differential. All right. We will have the highest temperature differential for the medium which is having lowest product of specific heat and mass flow rate. So, this is actually heat capacity rate. This m dot Cp, this is heat capacity rate. So, the fluid which is having lowest heat capacity rate, that will have the highest temperature increase. All right. Now, what could be the highest temperature increase? Let us say the cold fluid is having the lowest heat capacity rate. So, the highest temperature the cold fluid can reach is the inlet temperature of the hot fluid. It cannot have higher temperature than the inlet temperature of the hot fluid, because that will amount to violation of second law of thermodynamics. All right. So, it can have at best THI at the exit. It can have at best a temperature which is equal to THI at the exit. So, that gives us the ideal or the best temperature differential which we can get. Okay. But actual temperature differential will be TCO minus TCI. So, actual divided by the ideal, that will give us the effectiveness of the heat exchanger. All right. So, that is how we can have some sort of a merit or some sort of a performance criteria of the heat exchanger defined. Once we define that, then we know the performance criteria of the heat exchanger. So, if you do this, then these intermediate temperatures you can predict. All right. And then from there we can determine the cycle efficiency. So, basically one has to bring in some of the heat exchanger characteristics to analyze the cycle when there is a regenerator. So, this actually has got relationship with, I mean, this is relevant for heat transfer, which we are going to study, and this is relevant for gas turbine. So, that is why I wanted to spend little bit time. So, this is one of the ways by which we can increase the efficiency of the basic gas turbine cycle, and of course, without spending anything for the fuel, but the cycle become complex and we have to bring one extra equipment. So, regenerator has to be brought in, and most of the gas turbine power plant, particularly which are on stationary gas turbine power plant, they should have a regenerator to extract some of the waste heat. Of course, this regenerator or the waste heat which is recovered from the regenerator, it can be used for other purposes, like it can be used in a steam power plant also, but that is a different issue. Then what else we can do? we can do some other modification in the cycle. One of them is intercooling. We know that compressor is a very crucial part of the gas turbine power plant. Compressor is a very crucial part of the gas turbine power plant, because it takes away, it eats away lot of motive power developed by the turbine. That means, the power which is developed by the turbine, part of it, a large part of it is utilized for running the turbine compressor. So, somehow if we can make the compression process more efficient or less energy extensive, then we are gaining. And we know that a compressor, when we compress the gas, its temperature increases and further compression becomes difficult. So, instead of compressing the gas in one stage, if we can have multi-staging of the compressor, and in between two different stages or two successive stages, if we have intercooling, then we can gain in terms of power. So, how it can be done? I am first drawing the cycle diagram. So, let us say this is my PV diagram, and I am working between two pressure limits. These are the pressure limits. So, I have to start from this point, this is the initial point, but I will not go to the pressure at one stage. So, what I will do, I will initially compress, okay, and as I am compressing it along an isentropic path, the temperature of the gas is increasing, and then I will do intercooling. If it is perfect intercooling, then after intercooling, sorry, the arrow sign is the opposite direction. After intercooling, this temperature and this temperature, they are same, but perfect intercooling is not possible. So, we will have some intercooling, and then again we will have the compression up to the final pressure, and then combustion, of course, which is replaced by a constant pressure heat addition, and then expansion, and then constant pressure heat rejection. So, this is our PV diagram for the entire process. All right, then what we can show that if we could have followed compression in the same stage, we could have gone along this path, but here we have gone through this path. So, this much extra amount of work we are gaining or saving. All right, this much extra work we are gaining or saving. So, that is why by intercooling we are going to have some benefit, and well, I have shown only one stage of intercooling, that means compression by two stages, but it can be done in more stages, but it becomes complex. So, more than two intercooling generally is not done. Okay. So, we can have some benefit by intercooling the gas after one stage of compression. I am not drawing the block diagram. Basically, there will be two compressor, in between there will be an intercooler which will be cooled, where the gas will be cooled by a suitable medium. Then similarly, one can have the expansion also in different stages. So, if we have expansion of high pressure, high temperature gas in the, okay, let us draw the diagram, then it will be understandable. Let us draw without any intercooling. We have the PV diagram of the process. So, we are starting from here, we have gone to a very high pressure. At that pressure, we are having the combustion process, which is replaced by an ideal constant pressure heat addition. Then we are having the expansion. After expanding the hot product of combustion to certain pressure, intermediate pressure, what we will do? We will take it out of the turbine, and then we can reheat the gas. This is reheating. We can reheat the gas. That means it can be done like that. The combustion process we will have in two stages. Initially, we will not burn all the fuel in the incoming air stream. Part of the fuel will be burnt in the incoming air stream. Then the product of combustion, which is having still lot of oxygen content, that will be allowed to pass through a turbine, where partially its pressure will be reduced and its temperature will fall. Again, in that exhaust, we will burn the rest of the fuel utilizing the available oxygen there, and then it will be allowed to expand in a turbine, which can be a low pressure turbine, second stage of the turbine. So, here we can see that this much amount of extra work we are gaining. This much amount of extra work we are gaining by reheating. So, we can write Brayton cycle with reheat. So, what we have got? We can have intercooling, we can have reheat, and we can have regeneration. If all the three things are used together, then we will have some respectable figure as the efficiency of the cycle. Now, one interesting thing, let me combine reheat and intercooling together, then what we will get? This is the PV diagram. So, we are starting from this point, we have gone through the intercooling process, then second stage of compression, then expansion, reheat, and then expansion in the second stage of the turbine. All right. So, let us say this is the isothermal line, and let us say this is the isothermal line here. All right. So, one is the isothermal line here and another is the isothermal line here. So, after reheating we are coming back to the temperature, same temperature, and after intercooling we are coming back to the same temperature with which we have started our cycle, and here also after reheating we are coming back to the same temperature, same elevated temperature at which we have started our expansion. Okay. Now, if we show this process on TS diagram, how does it look? So, this is TS plane. So, what we have done, let us give some name, that will be easier. 1 to 2 compression, then 2 to 3 intercooling, 3 to 4 compression in the second stage, 4 to 5 constant pressure heat addition, 5 to 6 first stage of expansion, 6 to 7 reheating, 7 to 8 is expansion in the second stage, and 8 to 1 constant pressure heat rejection. Now, if we want to have this in our TS diagram, let us try to have it. So, let us say this is TA, one isotherm, this is TB, another isotherm. Two isotherms I have shown. So, initially I have started with 0.1. I have gone for isentropic expansion. Then I have gone for cooling. So, if I have gone for cooling and come back to the same temperature TA, so let us say our TA is somewhere here. So, this is our TA, well this is TA. So, we will come back somewhere here. All right. So, this is our intercooling process, and then we will go to 1, this is 2, this is 2 and this is 0.3 after intercooling, and then we will go to 4, again isentropic compression. 4 to 5 constant pressure heat addition, all right, and let us say this is Tb, the maximum temperature. Then we will have isentropic expansion 4 to 5, 5 to 6. Then I will have reheat process, which is constant pressure heat addition. So, this and this curve they will be parallel, and then we will have isentropic expansion. So, somewhere here, sorry. So, this is 6 to 7 and 7 to 8. Then I will have constant pressure heat rejection, is something like this. So, 1, 2, 3, 4, 5, 6, 7, 8. And the representation of the PV diagram is also shown in the TS diagram. Now, why I have done all this thing, it is like this. Let us say instead of one intercooling and one reheating, we have got very large number of intercooling stages and reheating stages. Then what we will get? What we will get is like this. PV, this is our one isotherm and this is our another isotherm. So, around this isotherm I will get reheating stages like this, and around this isotherm I will get the intercooling stages like this. Okay. So, this process if I continue, then this zigzag curve here and this zigzag curve here, they will coincide with isothermal processes, or they will coincide with the isotherms. Okay. So, what we will have then? We will have two constant pressure processes and two isotherm lines. So, two isothermal processes and two constant pressure processes we will have. Okay. Then what is the advantage? So, we will see that the efficiency will increase if these two processes are made closer to the isothermal processes. Then we will see that our cycle efficiency is increasing. So, that is why even if we cannot approach the isothermal processes, but we are trying to approach it, all right. So, even then with finite number of intercooling and reheating, we will have better efficiency, and that is what is done in gas turbine cycle. We will have intercooling as well as reheating, and when you are having intercooling and reheating, there are certain other advantages also. First thing, you can go for higher pressure ratio, okay, and in a single piece of equipment, pressure fluctuation is not very high. So, if we want to compress the gas in one compressor in single stage, then definitely you have to go for a very large pressure ratio. Okay. So, part of the compressor, it is subjected to small pressure, small value of pressure, part of it is very high value of pressure, means air is entering at a small pressure and then it is going out of a high pressure, and the entire thing you have to make it so that it can withstand that high value of pressure. Whereas, if you can divide it into 3 different stages, so the compressor which is handling the highest pressure, that can be made of thicker section, whereas you can have thinner section in other designs. So, these are some advantages are there. So, those are mechanical advantages, but other than that we have got lot of thermodynamic advantages, and that is why we want to have both intercooling and reheating. So, I think with this we will make is make an end to our discussion this chapter, that is your air standard cycles. And so, basically what we have done some sort of thermodynamic analysis for the cycles, and with this we can have the basic idea of the cycle performance, and from all the cycles we can also determine what is the efficiency, how much work is being done, and what are the variations possible with the cycle, so that their efficiency can be increased. Now, the last topic which we like to deal is heat transfer. Again, with the available time we cannot make much detailed discussion regarding heat transfer, but the basics I will try to cover. So, heat transfer, this is a very important topic for number of engineering disciplines, because we know that thermal energy is important as far as power production is concerned, production of low temperature is concerned. So, we have seen that in number of cycles we have got conversion between thermal energy into mechanical energy. Actually, at the end we want to have mechanical or electrical energy, but that can be produced or that can be converted from thermal energy. So, for thermal energy, whenever there is a temperature difference, we have got transfer of heat. That is why we should have some basic idea regarding the science of heat transfer. There are, these are these are known things, but even then for the continuity we should discuss that there are three modes of heat transfer. So, heat transfer modes, we have got three modes, and basically they are conduction, convection, and radiation. So, we will discuss one by one, and some of the basic laws of conduction, convection, radiation I would like to give you, and probably then some applications where we need to use them. Now, if we think of conduction, conduction is the mode of heat transfer where the thermal energy is transported from one molecule to the neighboring molecule without much bodily movement of the molecule itself. That it is like this, as the temperature increases, the molecule will have higher energy of vibration, and this vibrating molecule again it will transfer energy from the neighboring molecule. And of course, in metal the free electrons, they also take part in this type of exchange, energy exchange. So, without going into the details of the physics, which we do not need to know in a very detail, because we are analyzing the engineering aspect of heat transfer, we can see there are two modes of heat conduction. We have seen that mostly metals, they are very good conductors of heat, and they are also very good conductors of electricity. So, there is some sort of a similarity between the conduction of thermal energy and conduction of electricity, and in both the cases free electrons, they take a part, they take a very important part in transporting the energy. But again we have seen some of the non-metals, they are also good conductors. Some forms of carbon or graphite, they are also good conductors of heat. So, in that case we do not have enough free electrons, but the lattice vibration that takes part in the transportation of thermal energy. So, basically one can broadly say that there are two phenomena which are important for the thermal conduction of heat, that is, one is electron and another this lattice vibration, or it is known as phonon, P-H-O-N-O-N, phonon. So, these two are mainly important for the conductive heat transfer, and for the conduction heat transfer one can define a property which is known as conductivity. So, one can define a property conductivity. So, conductivity, it is like this: if we make a simple experiment where there is conduction along a particular direction, okay. Let us say we have got an infinite wall, plain wall like this, and we are maintaining one temperature T1 here, one temperature T2 here, and let us say T1 is greater than T2, and we have got a thickness L. Then we will see Q, the rate of heat transfer, let us put it capital Q, that will be proportional to T1 minus T2, that will be proportional to the area through which we are allowing the heat to pass, and that will be inversely proportional to L. So, we need a constant of proportionality. For the time being, let us put this is equal to K A T1 minus T2 by L. We will see that the amount of heat transferred will be different for different type of materials when the wall materials are different. So, the constant of proportionality, that is a function of the material, or that is a material property. This property we call as conductivity. This is conductivity. So, what I was discussing, that for conduction two phenomena are important, one is free electron and another is phonon. So, similarly we can define that conductivity is due to conductivity of electron and due to the conductivity of phonon. So, one can write this is a summation of Ke plus Kf, Kp, actually Pho, so Kp. And obviously, in case of metals, K electron is much higher, and that is why it is interesting to know that if we know the resistivity of the or electrical conductivity of the metals, there are physical laws by which it can be correlated with the thermal conductivity of the metal. So, there is some sort of a correspondence between the electrical conductivity and the thermal conductivity. All right. So, knowing this, what we can do is like this. The law which is the basics for analysis of conduction. So, this is known as Fourier's law of heat conduction. Heat conduction. So, this says Q dot is equal to minus K A dt dx. This is Fourier's law of heat conduction. Now, Fourier's law of heat conduction. So, what we can see, K is the conductivity of the material, A is the area, and T is the temperature, and X we are having the direction. There is a negative sign indicating that heat transfer will be in a direction in which temperature decreases. All right. That means, from high temperature to low temperature we will have transfer of heat. Now, this particular law one can apply for different cases and get the result by which one can determine the rate of heat transfer. So, we can take 3 different cases in case of, and it is this particular case what we are considering now, it is heat transfer only along a particular direction. Okay. So, unidirectional or one dimensional heat transfer. So, one can call it one dimensional heat transfer. Now, we can take different cases. So, plane wall, already we have discussed it. So, in the case of plane wall, this is the situation. So, what we will get, one of the wall is having a temperature T1 and another wall that is having a temperature T2, and let us say in our convention T1 is greater than T2, and then heat flow will take place in this direction. So, this is Q dot and this is L. So, Q dot is equal to K A T2 minus T1 into L. So, it is like this. How did you get this equation? How did you get this equation? One can have it like this. Q dot basic equation is minus K A dt dx. So, Q dot into dx is equal to minus K A dt. All right. Now, this integration can be done. Now, one can integrate it. That means, one can integrate it Q dot dx 1 to 2, that is equal to minus K A dt 1 to 2, 1 to 2, that means minus K A dt 1 to 2. Now, this integration can be done, and the result which I have shown, that can be obtained if K is independent, thermal conductivity is independent, and area is also constant. Area is also constant between point 1 and 2. So, then only this integration can be done, and that is what we have done. In the plane wall, we have assumed the area is constant, plane wall means area is constant, and we have also assumed K to be a constant. If K is a function of temperature, then what we could have done? Then this integration, knowing the functional relationship between K and temperature, one has to do this integration. And there are number of situations where K is not constant. This property, thermal conductivity, it is generally a temperature dependent property, and we have to determine this by integration. We cannot take K to be a constant if the temperature interval is high. Okay. So, in that case you cannot take K to be a constant, and then one has to go for the functional relationship between K and T. All right. With this, let us go for circular cylinder or annulus. So, let us put it cylindrical geometry. Cylindrical geometry, let us take the example that we have got an annulus and in the annulus one wall of the annulus we are keeping at T1, another wall we are keeping at T2. So, obviously, if T1 is greater than T2, then from the inside surface heat will get transferred to the outside surface, and this is a very common example, like we have got a steam pipe and over it we have got some insulation. So, obviously, from the outer surface of the pipe the heat will be heat will be flowing, or heat will be transferring to the outward direction, and obviously the outside temperature, where the temperature is low, probably it is at atmospheric condition, there will be flow of heat. So, in this case also we can use the same formula, and we assume the cylinder to be infinitely long. So, there is no end effect, and also we assume that temperatures are uniformly, inside wall is at uniform temperature of T1 and the outside wall is also at uniform temperature T2. Material property is not changing in the angular direction. So, in that case the heat flow will be only along the radial direction. Okay. So, one can write Q dot is equal to minus K A dt dx, that is nothing but minus K A dt dr along the radial direction. This is r, and let us say this is R1 and this is R2. All right, we have got two radii R1 and R2, inner radius and outer radius. So, in this case we can do the integration, but area is not constant, area is a function of radius, because what is the area through which heat is flowing? Vis-a-vis, if I have the plane wall, this is the area at the outer surface, this is the area somewhere in between, this is the area somewhere in between, and heat is flowing in this direction. But in the case of the cylindrical geometry, outer surface area, some intermediate area, then some other intermediate area. So, we can see that the intermediate area, that is different from the inside surface, that is different from the outside surface. In fact, as we go from the inside surface to the outside surface, intermediate area of cross section through which heat is flowing, that changes. Area of cross section through which heat is flowing, that changes. All right. And a general expression of the area, let us say at radius r, will be 2 pi r. Okay. into L, 2 pi r into L. All right. But along the L, try to visualize, along the L we have got infinitely long cylinder, otherwise this analysis is not valid, there will be end effect. So, sometimes we write 2 pi r assuming that L is equal to 1. So, we are doing for only unit length of the cylinder. So, heat transfer, whatever rate of heat transfer we will get, if we multiply it with required length, we will get. So, sometimes it is done like this. All right. So, if we do this, then we will have minus k into 2 pi r dt dr, and then we can have the integration q dot into 2 pi r dr, sorry 2 pi, let us go to the second page. Q dot is equal to minus k 2 pi r dt dr, and q dot into dr by r is equal to minus k into 2 pi dt. If we do the integration, then we will have q dot into ln r 2 by r1 r2 by r1, that is equal to minus k 2 pi T2 minus T1, that is equal to k 2 pi T1 minus T2, or finally q dot is equal to k into 2 pi T1 minus T2 divided by ln r2 by r1, or one can write taking the length into consideration, that is equal to k into 2 pi L T1 minus T2 divided by ln r2 by r1. So, this is what we get in case of a circular cylinder when thermal conductivity is constant. All right. So, I think let us take a small break and then again we will resume from here.